Hi friends, so today we start lecture 63 on our helicopter dynamics course, and today we are going to look at the torsion motion, but we are going to consider a flexible blade today, and we are going to derive the equation of motion for this blade and look at its natural frequencies and mode shapes. I'm Dr. Ranjan Ganguly. Now previously we considered rigid blades in torsion. But in reality, helicopter blades are flexible. If you have been to an air show and seen the blades, you will see that they are quite flexible, in fact, and therefore flexibility needs to be included when we are doing the modeling of the rotor blade, and that's what we are going to do today. So essentially, we know that the blade is going to twist around an axis, and this axis is the locus of all the shear center points, and this is known as the elastic axis, which we will call as EA. That's the acronym we are going to use. Now, to simplify the analysis and mathematical modeling, we are going to assume that this particular locus of points is a straight line and it coincides with the feathering axis. Now, the CG axis is different from the elastic axis in general cases, and it is going to lie somewhere behind the elastic axis. So we are going to assume a small distance there. So this is the diagram looking at the blade from the top. So you can see the twist motion here given by theta. The EA is somewhere here and theta is taking place around this EA, and the CG axis is further down compared to the EA. And also we are going to use some nomenclature such as R is a general location, rho is another location in the radial direction, and d rho is the particular small piece of the blade which we are going to consider when we derive our equations. So this is in the radial direction. So theta is the pitch change in a given station, and now we are going to calculate the forces and moments which act at a blade section. And again, as I mentioned before, the distance between the EA and the CG is xi, and this is going to play a big role in this particular problem. So let's look at the airfoil section. So you can see the EA here, the CG here. The distance between the EA and the CG is given by x subscript I. This is the angle theta. Now there are certain forces which are going to act on this section if we are only considering the torsional motion. So one is the propeller moment, that is around EA. So that is I theta rotation square theta d rho. Then you are going to have an inertia force, that is m naught xi theta double dot d rho. And then there is also going to be one more moment, and this is around the CG, that is I0 theta double dot d rho. So these are the three forces which are acting, and we see that these forces and moments are essentially restoring, that they are trying to bring the airfoil section back or bring the theta downwards. Now in contrast to this, there is a force created by the fluid mechanics which is acting to bring the theta up, that is m theta d rho. So these are the four forces and moments which are acting at a given section of length d rho. So again, to summarize this particular fact which we discussed in the previous slide, we have a force and the arm is x of I. There is a torque, that is I0 theta double dot d rho about CG axis. There is a propeller moment around the EA, and there is a aerodynamic moment m theta d rho around EA again. So we are going to take these forces and write the equation of motion. So that's the moment. So that's the torsional moment at a station R. So m of r is then going to be the integral of small r to capital R, and the net of all the moments which act at that particular section into d rho. So remember, that is a section of size d rho, and rho is varying from small r to capital R. Now, if we observe this very closely, we will again see that the three negative moment components are the restoring components, and the one which acts to increase the moment is m theta. So now we use a certain fact from geometry or basic mechanics, that is I theta is I0 plus m naught xi square. So this is by simply moving the moment by this distance here, I can write this equation, and therefore I can write the term I0 and mx square as I theta. Okay, so the theta double dot term also includes I theta, which I have written here. So now this term has been expressed in a simpler form. All the things are in terms of I theta, and always remember that if there is an xi, then you can move between I theta and I0 by using this particular formula. So now we have got the torsional moment, and now we need to relate it to the torsional stiffness. So from the engineering torsion theory for slender bars, we have the equation mr is gj d theta by dr. That is gj d phi by dr, where phi is the torsional deflection. So now from this moment, I can get the equation of motion for torsion, and I need to correlate these two equations here. So I can clearly see that if I were to differentiate mr, then I would get the term which is just inside the integral without the d rho. So we are going to do that next. So we take a derivative of mr with respect to r, and so we get this equation here. Okay. So here now I have been able to relate the torsional stiffness Gj, the elastic twist phi, with the moments which act on that particular cross section. So I can write this equation in this form by bringing the forcing function to the right hand side, that is m theta, that is essentially coming from the fluid mechanics of the problem. And on the left hand side I have the flexural stiffness term, that is the Gj term. I have the inertia term involving theta double dot, and I also have the propeller moment type of term, as well as the term involving I0 theta double dot here. So the I0 theta double dot term is here, and this is the propeller moment term. So all the stiffness here is actually coming from the propeller moment. Now, to solve this equation, I need two boundary conditions because this essentially has second derivative with respect to r. So let us look at one case. Now typically the pitch link is located at some distance RA from the rotational center. So from R is 0 to RA, the blade is torsionally rigid. So I can write the boundary conditions as follows. At R is RA, which is some small distance from the rotational center, Gj theta dash is going to be minus k theta into theta minus theta con. So this is like a spring, okay? And then at R is R, that is at the tip of the blade, Gj theta dash is going to be 0. So that's the free end of the beam or the blade. Now if we had a cantilever blade, then R is 0, theta would be 0, that's the fixed condition. And at R is R, Gj theta dash would be 0, that is the free condition. Now typically Gj is not going to be uniform. You have seen the blades and you know that they are not uniform, but it is easier to solve the equation of motion for a uniform blade, and therefore to get a baseline solution we are going to do that. So let us again look at this torsional equation, and now I have dropped the forcing term because we are primarily interested in just solving this equation and finding the frequencies and the mode shapes. So if you have a uniform blade, it is easy to solve, but the moment you have a non-uniform blade, that is your Gj is a function of R, this equation becomes quite difficult to solve, and you would need to use some kind of approximate method like Rayleigh rate, Galerkin, or FEM to essentially find the natural frequencies and mode shape for even this very simple model of a blade only in torsion. So we are going to presume a simpler blade to get a solution. So we will say that let rotation speed be 0 and Gj be constant. In that case, I get this simple equation here, which some of you may recognize is the equation of a bar in torsion. So I can immediately take this equation here, and it's a constant coefficient differential equation. I theta Gj are both constants, and therefore I can assume the solution of the form some function of r and then the harmonic motion, which is a complex sinusoid. So I can get the theta double dot, and that gives me the typical harmonic motion. I substitute theta and theta double dot into the differential equation, so I get this equation here. And then I remove the term involving the exponential, which essentially cannot be 0. So this particular function should be 0. Okay. So now this is one more differential equation. I have managed to eliminate time from it by using that separation of variables and presuming the harmonic content. Now to solve this constant coefficient differential equation, I assume theta is EPR. So this is theta bar, which we have introduced as an intermediate variable. And then we take the second derivative of this with respect to r. We substitute it here, and because EPR is not going to be 0, I can get P in this form here. And now I get P is plus minus I lambda, where lambda is expressed in terms of the natural frequency, the I theta, G and J. So Gj is the torsional stiffness of the blade or the beam. So I can solve this theta bar because you saw that it was plus minus I lambda. I can write it as a cos and a sine, and I also know that the natural frequency can be written in this form as Gj I theta and then lambda. And now as usual I need to find lambda, and to find lambda I need to put in the boundary conditions, because that's how the system gets to know its physics. Till now the system is completely mathematical. So let's assume a cantilever blade. So at r is 0, theta is 0. At r is capital R, theta dash is 0. So that's the tip of the blade, r is capital R, that's the root of the blade, r is 0. I substitute both into this solution here. So you can clearly see that r is 0, theta is 0 gives me that a would be 0. Okay, because I put 0 here, I put 0, 0 here, this term goes out but a remains here, so a equals 0. So that's one of them is gone. So then theta bar r is going to be b sine lambda r. So that's what we have, and therefore I can get the equation for theta dash here. Theta dash would be b lambda cos lambda r by differentiating, and so theta bar r is going to be b lambda cos lambda capital R is 0. Now for this to be true in a non-trivial sense, that is, I don't want a solution like lambda equal to 0 or b equal to 0, cos of lambda r should be 0, and therefore I get a plethora of solutions out here. So lambda r could be 90 degrees, that is pi by 2. We are all familiar with that cos 90 degrees is 0. It could also be 3 pi by 2, and in general it could be pi j minus half. So for example, if j would be 1, I get the first solution and so on. So these are essentially the solutions of this characteristic equation cos lambda r equal to 0, and they are going to give us the natural frequencies for this problem. So if I am dealing with the first mode, lambda 1 would be pi by 2r, and therefore the frequency would be pi by 2r root Gj by I theta. So that would essentially give you the frequency of the non-rotating uniform blade in torsion. And again, that can be used as a way to check any numerical result. You can set your rotation speed to 0 and assume a uniform beam and see if you are getting this kind of exact solution. Secondarily, we will see we can use the mode shapes of this beam for methods such as Galerkin, Rayleigh, etc. for doing approximate work. So talking about the mode shapes of this beam are going to be theta is sine lambda jr, where lambda corresponds to the particular frequency you are concerned with. So again, you know this is a very simple function. It's a simple sinusoid. So you know that these are going to be orthogonal. And as usual, the mode shapes are normal to each other. In this case, it is very easy to see that. So this was my take today on the elastic torsion motion, and we saw that this equation is one of the simpler equations. In this case, it is simpler than the ones for flap and lag bending because those involve the fourth derivative of the value w. Here you are dealing with second derivatives and the equation is somewhat simpler. So I will end this lecture today and I will see you in my next video. See you then.